Welcome. In this video I'm going to show you how to determine the chi-square value for a Pearson chi-square goodness of fit test manually using a chi-square distribution table. The formula for a chi-square value is as follows, which might look very frightening to some. But don't worry, we'll go over this one by one using an example. In the example, I have a few marital categories and their observed frequencies from the sample. The first letter you might actually notice in the formula is this C, and that C is short for the number of categories. So in this example I have 1, 2, 3, 4 and then actually 5 different categories. So C in my case equals 5. So if we replace this C already with a 5, we got rid of one of those symbols in there. The next symbol that you might notice is this OI. That's actually short for the observed frequencies or the observed counts. So my frequency column I can also label as OI. The next one you might actually see are these, the EI, and that's short for the expected count. Now, depending on your situation, you might actually have a specific expected count for each categories, or as in my example, I'm just going to assume that I expect that each of the categories was chosen equally likely. In that case, I can actually use a small formula to calculate the expected value, where n in this case is the total number of respondents. So in my case, that would be that 1941. So my expected frequencies will be that 1941 divided that by the number of categories 5, and that will turn out to be 388.2. That will then be the expected count for each category, so I can add that next to my observed counts, and I'll label that EI. Now, to do the rest of this formula, where we're actually going to do the calculations, I'll show you on the next slide. So on the previous slide, we've seen the observed frequencies and the expected frequencies, and now it's time to move on with that big formula. In the formula, the first thing we see here is that we actually need to subtract the observed from the expected frequencies. And we need to do that for each category. So I've done so here. So the first one is the 972. That's this one up here. And then minus the expected frequency of 388.2, and that gives me 583.8. And I've done so for each of the categories, and they nicely sum up to 0. So that can be a small check to do if you're performing this manually. Then the next thing you notice is that we need to square these results. So I'm simply going to take this column and actually square the results. So the same values, but then simply squared. So SQ for squared. So notice though that minus 207.2, notice the parentheses. So the minus actually gets squared as well. So that's why here it's plus 42,931. So sometimes people actually do this in one go. They simply type this one in on their calculator, then type on your calculator the equal sign, and then immediately type the square. Now for those who don't know, a square is simply just a multiplication of a number with itself. So for example, this minus 74.2 squared means minus 74.2 times minus 74.2. Then the next thing we need to do is divide that each of these results by the expected frequency, expected count. So this one then divided by that expected count. I've done so already to make the calculations a little bit faster. So this big number up here gets then divided by the original expected count. That's exactly what I've done up here. And those numbers have quite some decimals, so I've rounded them. So that's why you see the approximate symbol up here. So we're kind of done with doing this for each category, and then you're probably wondering, what is that weird looking E up here? That's actually a summation sign. It says to sum up starting for I is 1, so that's in this case the first category, up till the number of categories. So we're going to simply sum up all of those results. So if we simply say here, well, hop and add these up, plus, then we should actually get our chi-square value. So I've done so here below. That results in 1249.13, and that is then that chi-square value. So finally, our chi-square value is 1249.13, which is actually also the value we've seen in the SPSS and the R output and the Excel output. So the chi-square value calculation in itself is actually done in 4 steps. The first one is to determine the difference between the observed and the expected counts. In formula notation, it would be like this. Then you square those results. That will look like this in the formula. Then you divide each of those results by the corresponding expected count. So we get this part in the formula. And last but not least, you add them all up. So sum up all the results of that previous step, and in formula notation we then actually get the formula for the chi-square value. Before we can find the significance or the p-value of a specific chi-square value, we also need to know the degrees of freedom. Now don't worry, this formula is a lot easier than the previous one. It's actually c minus 1, and c we already know, that's the number of categories. So in my example, I had 5 categories, so my degrees of freedom is simply 5 minus 1, which equals 4. To finally find then the significance of the chi-square value, we need to look it up in some kind of table. Now, most tables are so-called right-tailed, but you might want to double check. On the next slide, I'll discuss what to do if it's left-tailed. The first thing to do is look in the row, so each of this is a row, so you're actually gonna look like this, and you're gonna try to find the row that corresponds to the degrees of freedom, because this one is about degrees of freedom. And in the example that was 4, so when we look in here we find 4 up here, so I'm going to be looking into this row, and I'll highlight it as well. Then you need to look for your chi-square value in that row. And it depends, and there are kind of like 4 different situations that you then actually might have. The first one might be that you find the exact chi-square value. So for example, if our chi-square value would have been 9.488, then we would have found 9.488. And then the significance will actually be the number corresponding to the alpha level on top, so that's going to be the 0.05 in this case. If, however, the chi-square value falls between 2 numbers, so for example it's going to be 8, then it's going to fall between these 2 numbers, and in that case the significance is also going to be simply between these 2 numbers, so somewhere between 0.05 and 0.1. Another option might be that the chi-square value is greater than the first value. So in our case, we had 1200 and something, so that's bigger than the first number. In that case, we can simply report that the significance will be below the 0.005. Yet another option might actually be that the chi-square value is smaller than the last value. So if, for example, our chi-square value would have been 0.1, then it would have been smaller even than this one. And in that case, the significance will be above the 0.995. If for some reason you have a left-tailed distribution table, in that case, everything kind of flips around. So in this case, as you might notice, it has a left tail probabilities. The idea remains the same, but in essence, what you actually do is for your significance, you do 1 minus the alpha level then. So you again look up the row of the corresponding degrees of freedom. So in our case that was 4, so I'll still be looking into this row now. And I'll highlight the row to make life a bit easier. And again, find the chi-square value, and we now have again 4 options, either the exact chi-square value, so for example we find 0.711, then the significance will actually be 1 minus the 0.05, so that would be 0.95. If it falls between, you get the same thing again actually, so let's say it falls somewhere between these two values. In that case, it's going to be somewhere between 1 minus 0.025, so that's 0.975, and 0.95, 1 minus this one. And then we get the chi-square value is smaller than the first value, so if it's smaller than 0.2, then the significance is going to be greater than 1 minus this one. And if it's actually going to be greater than the last value, so bigger than 14.86, then we actually do 1 minus this one, and the significance will be less than 0.005. As a final note, it might happen that your degrees of freedom is not actually shown in the table. You could then perhaps use the lowest degrees of freedom close to it. That would be more like a worst case scenario. Some might actually recommend to use linear interpolation or some optimized interpolation, or perhaps even another distribution doing an approximation of it. That's all quite specific, so you might want to check with your professor. And if you're really interested, let me know in the comments, then I might actually consider making a video on this. And one other thing is that you sometimes might run into this formula. If all the expected counts are equal, as was in the example, then you can actually use a slightly alternative formula. On the next slide, I'll show you the math on why this actually works, but I just wanted to throw it in there just in case you run across it. All right, that was mainly it. Stay tuned if you want to see the proof for the formula, and otherwise, thank you for watching. All right, so here is that proof. If the expected counts are indeed simply done by n over c, then the chi-square value is actually, of course, simply the e. So because e is then constant, the expected counts. We can then work out the parentheses. That's what I've done from here to here. Then I actually split up the fraction. So that's what's done here. And then I can actually cross out this e against that one. And I can cross out this one against that one, and that gives me here this one. Then the summation here is going to be split up into 3 parts. I'm going to sum up this, then separately sum up this, and then separately sum up that. That's what's done here. Then, because this no longer has i's in it, I can simply replace that by c times e. And also here I have a 2 times, which I can simply actually move up in front of it, and that's what I've done here. Now because because we have the n divided by c equals e, we can also say that c times e will actually give me n. So c times e actually gives n, and the sum of the observed counts is of course the same as the total sample, so also this part actually gets simply to be n. And since minus 2 times n is the same, plus n is the same as minus 1 times n, we are left here. And that's actually all there is to it. Also here the e is actually not using the indices, so we can do the division by e. We can actually move that out of the summation, and that's what was done up here. So that's a quick proof for this formula.